Alright, today's section is about trig substitution. This is a way of doing integrals that involve the square roots of quadratics, which actually come up quite a bit, especially when you're doing distances, but in other situations as well. So we're going to be looking at integrals involving the square root of quadratics, in particular forms that look like these, and variations. So a is a constant in this situation, and x is the variable we would be integrating. So anytime you have a quadratic under the square root, you can complete the square and do other things to get it to look like a variant of one of these three. And we'll see how to deal with them in more detail in class. But the idea with trig substitution is we're going to use trig identities. Trig identities have these particular trig identities have these lovely quadratic forms. The one everybody knows is sine squared plus cosine squared equals 1. If you divide that whole equation by cosine squared, you get the blue equation, tangent squared plus 1 equals secant squared. And if you divide the top one by sine squared, you get the bottom equation, 1 plus cotangent squared equals cosecant squared. And we'll use these trig identities, use substitution, etc., and we'll turn the integral in its original form, which involves the square root of a quadratic, into an integral involving trig functions, which then, of course, we'll have to do that integral, and so sometimes that may involve techniques from last section on trig integrals. So for this video, I just want to show you an example of how this works. Say I want to integrate the square root of 4 minus x squared over x squared with respect to x. Now from the last slide, I had a square root of a squared minus x squared as one option. That's this kind, a number squared minus x squared. So the number a is 2, because that 4 is really a 2 squared. So you'll see 2's a lot here. So here's what we do. We do a substitution, but instead of the kind we're used to where we say let u equal some x stuff, we're going to let x equal something. And we're going to let x equal 2 times sine of theta. So theta is our new variable that's being introduced here. If x equals 2 sine theta, then dx is the derivative 2 cosine theta times d theta. So we can plug that in for dx. And this square root of a quadratic is going to turn out to be something nice, which is the whole point of the substitution. The square root of 4 minus x squared, replace x with 2 sine x, so I have the square root of 4 minus 4 sine squared of theta. Factor that 4 out, and we notice we have a 1 minus sine squared theta. From the trig identity, that's the same as cosine squared theta. And then I have a square root of 4 times the square root of cosine squared theta, so I get 2 times cosine theta. So I can replace that square root of 4 minus x squared with a 2 cosine theta. Now, technically there should be some extra stuff written where these two asterisks are. I'm not going to focus on that too much, but when you do this substitution, you technically need to restrict what angles theta can be. So when you do a sine substitution like this, you have to say theta is in between negative pi over 2 and positive pi over 2, just like when we were dealing with arc sines. And when you do that, that forces cosine to be positive, which means that I really can take the square root of cosine squared and say it's just cosine. I don't need to worry about absolute values. But these are always chosen so that they'll work out, so we don't need to worry about it too much. So here I've replaced everything in the integral with what it's equal to in terms of cosine. That square root on the numerator I just figured out was 2 cosine theta. The dx I figured out was 2 cosine theta d theta. And the x squared in the denominator is just that x expression, 2 sine theta, squared. So the 2 squared becomes 4, and then I have a sine squared. I can simplify this a bit. The 2 times 2 over 4 cancels out, and I just have a cosine squared on top and a sine squared on the bottom. Cosine over sine is cotangent, so this is really just cotangent of theta squared. Cotangent squared of theta that I'm integrating. I don't know a function whose derivative is cotangent, but we do have this other trig identity that cotangent squared is cosecant squared minus 1. So I substitute that in. And that's easy to integrate. Right? A function whose derivative is cosecant squared is negative cotangent, and a function whose derivative is 1 is just the variable, which in this case is theta, because I'm integrating d theta. So negative cotangent theta minus theta plus a constant, because it's an indefinite integral. Right, so that's the integral done. However, it's in terms of theta. Since my original integral was in terms of x, I want my answer to be in terms of x. That is, I'm looking for a thing with x's in it, that when you take its derivative, you'll get the square root of 4 minus x squared over x squared. So I need to go back to my original x variable, and to do that I will realize that if x equals 2 sine theta, I can divide by 2 and I get sine of theta equals x over 2. So this tells me something about theta. It lets me draw a picture, just like we did with our inverse trickery stuff in chapter 6. This lets me draw a triangle, a right triangle, with theta as one of the angles, and I know that sine of theta is x over 2. Sine is opposite over hypotenuse, so I'm going to let the opposite side be x and the hypotenuse be 2. And now this is a picture of an angle theta, and sine of theta is x over 2. Well, I want to know what cotangent of theta is, so I have to fill in the third side of this triangle. I can do that using the Pythagorean theorem. X squared plus the third side squared equals 2 squared. And I get that third side is the square root of 4 minus x squared. As a general rule, your third side of the triangle, when you do problems like this, should bear some relationship to the square root thing that you started out trying to integrate. So I have the three sides of this right triangle, and I want to know what cotangent of theta is. And cotangent of theta is the adjacent side over the opposite side, so that's the square root side over the x side. So cotangent theta is the square root of 4 minus x squared over x. So that's what's going to go instead of cotangent theta, so it'll have x's in it. And then instead of theta, I realized that, well, if sine of theta equals x over 2, theta is an angle whose sine is x over 2, and that means theta is the arc sine, or the inverse sine, of x over 2. So I replace cotangent theta with this square root expression, and I replace theta with the inverse sine of x over 2, or the arc sine of x over 2. So here is my answer, and you can check if you take the derivative of this thing, as unpleasant as it would be, you should end up with the square root of 4 minus x squared over x squared. So, a couple of things I want to emphasize from this example. That is, this is a substitution, but instead of the kind we've done before, where u equals some x stuff, we are not saying theta equals some x stuff, we're saying x equals some theta stuff. Right? And from that we get dx, and from that we can also figure out the square root of the quadratic that we're dealing with. Okay. And then put everything into the integral, turn it into a theta integral, do the integral, and then go back to the variable x that we started with. So this is going to be a quick review, because sometimes you need to complete the square to use trig substitution, and some of you may not have done that for a long time, or maybe ever. So I'm just going to show you a couple of quick examples. Say your integral involved the square root of x squared minus 6x plus 8. We would like to rewrite that as some x thing squared plus or minus a number under the square root. Right? So the forms we'll be able to deal with are x squared plus a squared, x squared minus a squared, and so on. So I need a x thing squared. Right now I've got x squared, but then I've also got this minus 6x messing things up. So here's what we do. We think about x squared minus 6x plus 8, and we think, well, if there were some x thing squared, what would it be? Because of that minus 6, you take half of it, and it turns out that it would have to be x minus 3 quantity squared. So let's see what x minus 3 squared is. Well, when you multiply it out, it's x squared minus 6x plus 9. That means if I had a plus 9 next to that x squared minus 6x, I would have this perfect square. So I can just put that in. But I don't want to change the value of my quadratic, so if I add a plus 9, I need to put in a minus 9 as well, so that works out to be the same as what it was originally. So you stick in a plus 9 by the x's, and stick in a minus 9 by the number, the constant. And so what we have is that x squared minus 6x plus 9 is x minus 3 squared. And the plus 8 minus 9 works out to minus 1. So that the quadratic under the square root turns out to be the same as x minus 3 squared minus 1. Here's another example. Say under our square root we had 12 minus x squared minus 10x. This is different because the x squared is negative. So instead of it being x stuff squared plus or minus a number, it's going to be a number minus x stuff squared. But what x stuff is going to be squared, and what's the number? That's the question. So first I rewrite it as the number 12 minus, and then I want to have my x stuff in parentheses, which means I factor a minus out of all the x stuff that's currently there. So instead of minus x squared, I have a minus on the outside and an x squared on the inside. Instead of minus 10x, I have a minus on the outside and a plus 10x on the inside. And then I think, okay, what would make x squared plus 10x plus something a perfect square? That would have to be x plus 5 squared to get the 10. And so when you check out what x plus 5 squared is, you get x squared plus 10x plus the number 25. So we put that 25 in the parentheses where we need it to make a perfect square, but realize that what we've really just done is put in a minus 25, because that minus sign outside the parentheses will turn it into a minus 25. So since I put in a minus 25, I need to put in a plus 25 to balance it out. So now I have an expression that is equal to the thing I started with, that 12 minus x squared minus 10x, but now it looks like 12 plus 25 minus quantity x squared plus 10x plus 25. Okay, that's the same expression, it equals the same thing, but it's written in a way that now I can say, well, 12 plus 25 is 37, and the stuff in parentheses is x plus 5 squared. So that expression is 37 minus the quantity x plus 5 squared. Again, this is exactly the same if you multiply it out and simplify as 12 minus x squared minus 10x. It's just written in a way that we can see it is a number minus x stuff squared. Okay, so this is called completing the square. And when you have to do this for these integrals, then instead of letting x equal 2 sine theta or whatever, you let the whole squared thing equal the trig stuff. So in the first situation, x minus 3 is what's squared, so x minus 3 would equal some trig stuff with theta in it. In the second situation, x plus 5 would equal the trig stuff, and then you do your substitution and do your integral. Okay, so I just wanted to point out completing a square in case you guys haven't seen it recently. Here's the video question. Let's say I'm doing an integral and it involves this. I've already completed the square for you. It's the square root of the number 25 minus the quantity of x plus 2 squared. I'm telling you that what you want to do in this situation is to substitute x plus 2 equals 5 sine theta. Now, just like in the example before, what I would like you to do is figure out what dx will equal and what that square root thing will equal. Right? This square root thing that we have to deal with in our integral. So find dx and find the square root of 25 minus the quantity x plus 2 squared. Bring that to class and I will see you there.